So you saw how we were able to find the shortest path from one node to every other node using the Dijkstra's algorithm. Now let's take a look at the Bellman-Ford algorithm. And this, we can attach the code Ford 62. This also finds the shortest path from a given node, but here subject to the constraint that the path contains at most one link. Then we find the shortest path with the constraint of the path of at most two links, so etc. So we can do one link, two link, three link. Here also we define some parameters. S is a source node, and we have Wij just like in Dijkstra's algorithm. We have the Wii, that cost is 0. Then we have Wij when there's no direct connection, that is infinity. Then we expect that when there's direct connection, Wij should be greater than or equal to 0. Then we introduce an H, which is the maximum number of links in a path at the current stage of the algorithm. Then here also we have the L of n, but here we'll use L subscript H to differentiate between Bellman-Ford and Dijkstra's. And this is the cost of least cost path from S to N, but here under the constraint of no more than H link. Take your time also and go through the algorithms. We have the initialization for step 1. We have update for step 2. Now, with Bellman-Ford, we collect N with predecessor node J that achieves some minimum threshold. We eliminate any connection of N with different predecessor node formed during an earlier iteration. Here, Bellman-Ford, we are going to be doing iterating through the number of nodes that we have. So based on the number of nodes, we will know how many iterations to perform. Now for each iteration of steps 2, with say h equals to k, and for each destination node n, the algorithm compares path from S to N of length k equals to 1 with path from previous iterations. And if the previous path is shorter, it is retained. Otherwise, the new path is defined. So I'm going to take you through another example that is going to simplify the Bellman-Ford algorithm for you. See you. Hello. Now, let's take a look at how Bellman-Ford algorithm will function on this graph. So we have a graph with a starting node of S and a finishing node of F. Now, one thing about the Bellman-Ford algorithm is that it helps us to calculate negative edges. So it takes into consideration negative edges. So you can realize that from S to C, we have -2. Now, with Bellman-Ford, we need to do a number of iterations before coming out with the shortest path and the least cost. Now, to do that, we take note of the number of nodes that we have. So here we have 1, 2, 3, 4, 5, 6 nodes. How do we know the number of iterations to do? Now, this is given by n minus 1. So the number of iteration is given by n equals to n minus 1, sorry, where n is the number of nodes in the network. So currently I have 1, 2, 3, 4, 5, 6 nodes. So it means that I have 6 minus 1, which gives us 5. It means I'm supposed to perform 5 iterations before I get to the end of Bellman-Ford's algorithm. Now let's take a look at how to go about it. I also draw my table, and this time around I have the number of iteration here. Of course, we have the initial one 0. Then I have my nodes S, A, B, C. C, D, F. So just like in Dexter's algorithm, we are going to set the initial cost to every node as infinity. Of course, the starting node is 0. Now, this is what Bellman-Ford algorithm is about. From the starting node, remember there's a constraint that we need to find the path of either one link or two link or more, or the H link. So from S, there are two outgoing links to A and to C. So from S, I am going to calculate the cost of going to A. To do that, don't forget the cost at S is 0. So just like we did in Dexter's algorithm, I'll add 0 to 5. That gives me 5. Now 5 compared to the current value at A is 5. 5 is smaller. So I'll cancel this and put 5 by it. Now, and this is coming from, so this is the first iteration I'm doing. So I put 1 there. That's the first iteration. And the predecessor is from S. So I put S beneath it. I take that again. From S to A, to cost me 5. 5 plus 0 is 5. Compared to the current cost at A is infinity. 5 is smaller, so I take the 5. So I cancel the infinity and put the 5 there. Its predecessor is S. At the same time, I can update C. Now C has -2. -2 plus 0 is -2. Now -2 compared to infinity is -2, because -2 is smaller than infinity or positive infinity. So I cancel this and put -2, and that is also coming from S. So once I have finished with all the outgoing link of the starting node, I move to the next node, which is A. At A, there's only one outgoing link, and that is going to B. So it means that I'm going to update the cost at B. Now, I already know the cost at A, which is 5, coming from S. So to go to B, I have 1. 1 plus 5 is 6. Now, where is B? This is B. So 6 is less than infinity. So I cancel this and put 6. And that is coming from A. I guess you are following. Now, A has only one outgoing link. So from A, I go to B. Notice what we are doing. I'm traversing through all the nodes for the first iteration. So from B, B has, okay, there's an arrow here and there's an arrow here. Take note. So B has 3 outgoing links. 1 to C, 1 to D, and 1 to F. Okay. So at B, we already know the cost at B, which is 6. Now we want to update the cost at C. Now note that the initial cost at C is -2. So moving from B to C, it costs us 2. 2 plus 6 is 8. Now 8 compared to -2, 8 is way bigger than -2. So we still maintain the -2. Now B to D, the cost is 7. 7 plus 6 is 13. Now 13 is smaller than infinity. So I update D, cost of 13, and this is coming from B. Then B to F, the cost is 3. 3 plus 6, that gives us a 9. 9 compared to infinity, we'll take the 9. and that is coming from B. Guess you are following. Now from B, we move to C. C has only one outgoing link. So, and the cost is 3. The initial cost at C is 2. So, 3 plus 2, that will give us 1. And we are updating D. Now, 1 compared to 13, of course, we will choose 1. So, I cancel the 13 and put 1 there. And that is coming from C. So, I cancel the B and put C there. I repeat that. Now, from C, we have only one outgoing link to D at a cost of 3. But the cost at C is negative 2. So, to go to D, we have 3 plus negative 2, and that will give us 1. But the cost at D was 13. And 1 is less than 13. So, we cancel the 13 and put 1 there. And the predecessor it's coming from is C. So, we are done with C. Now, let's go to D. D also has one outgoing link to F at a cost of 10. Now, 10 plus 1 is 11. Now, 11 is bigger than 9. So, we still maintain that. Now, F is the finishing node. So, there's no update. And this brings us to the end of the first iteration. Don't forget, we are supposed to do 5 iterations. So, we go to the next iteration. Now, mind you, after the first iteration, the cost at S is 0, that at A is 5, that at B is 6, that at C is negative 2, D is 1, and F is 9. Okay. So now, we still go through the same process. From S to A is 5. 5 plus 0 is 5. We already have 5 there, so it doesn't change. What about to C? It's 0 plus negative 2, which is negative 2. Negative 2 compared to the cost at B. No, the cost at C, sorry, is still negative 2. So we maintain negative 2. So it means at A, this is still, at A is still coming from the source. And this is also maintaining its predecessor. Now let's go to A. A has one outgoing link to B at a cost of 1. 1 plus 5 is 6. Fortunately, the cost at 6 is still 6, so it doesn't change. Then let's go to B. B, the cost at B is 6. Now, 6 plus 2 is 8. So we are updating C. Now, the cost at C is negative 2. So 8 is bigger than negative 2. So C doesn't change. Let's see D. D has a cost already 1. 6 plus 7 is 13. 13 is way bigger than 1. So we still maintain that. Then let's take from B to F. B to F, we have what? We have 3. 3 plus 6, that will give us a 9. And it's still the same. Okay, so we are done with B. Now let's go to C. Now C, the cost at C is negative 2. The cost of the link is 3. So 3 plus negative 2, we are getting a 1. So updating D, D is already having 1, so it doesn't change. That's coming from C. Now C has a cost to A. Oh, okay. Now let's look at our initial first iteration from C. Okay, take note. Now from C, we had C to A. There's a link here. We forgot that. And that's at a cost of 2. 2 plus 2 is 0. 0 compared to this is what? Is 0. So it means 5 would have gone to 0 and this would have changed to C. Okay. So it means when we come back, this is to be 0 and 0 plus 5 is 5. 5 compared to 0 is 0. So it means this also changes to C. Good. So in the second iteration, we have C to this again. Of course, we'll still maintain RC. Now, let's look at C to D. Of course, we've already done that. Now, let's do from D. D, we have a cost of 1. Then 1 plus, so from D we have one outgoing link to F. So 1 plus 10, that gives us 11. 11 compared to 9, we still maintain that. So this is still B. Okay, then we go to F. Of course, it means F is still there. D is also still 1. So this brings us to the end of the second iteration. So we go to the third iteration. Okay, so let's update our link. So we have 0, we have 6, we have -2, we have 1, and we have 9. Let's look at the third iteration. So we have S going to A. 5 plus 0 is 5. Compared to 0, we have 0. We still maintain. This to C, we have 0 plus -2. That is -2. -2 compared to -2. We still maintain that. And that is S. We are done with S. We go to A. A has one outgoing link to B. Now 0 plus 1 will give us 1. Now 1 compared to 6 is 1 is smaller than 6. So we are going to update B to 1, and that is coming from A. Have you seen that? Okay. So now the current cost at B is 1. Okay. Now at B, we want to update C. So we have 1 plus 2, which is 3. 3 compared to -2. We'll still maintain that. Then B to D. We have 1. 1 plus 7 is 8. And 8 compared to 1, we still maintain that. Then we have B to F. Now we have 1 plus 3, which is 4. Okay? Now 4 compared to 9, we'll choose 4 over 9. And that is coming from B. So we have D. Okay, so B to D. I think there's a problem here. But let's continue. So this brings us to the end of the third iteration. Let's try the fourth iteration. So we have A not changing, still maintaining C, then B to A, we have 0 plus 1, 1, so it's still the same. Then at B, we have 1 plus 2, which is 3. As compared to C, we still maintain. Then to D, B to D, we have, that will be 1 plus 7, which is also the same, we maintain. Then we have the F also doesn't change, so we maintain. We move to C, the same thing, the values doesn't change. D, the values don't change. Now, we expected to do 5 iterations, but after a number of iterations, if the values don't change, then you can stop at that iteration, and that will give you the shortest distance at that cost. But you can continue with the 5th iteration, and you are sure to get the same values. Run through it and be sure. So if you want to find the shortest distance from, of course, here we already have our S there. So let's see the shortest distance to F. So to F, the cost is 4. Now to F, we need to come from B. Then from B, we need to come from A. From B, we need to come from A. Then from A, we need to come from C. Then from C, we go to the source, S. So we have S, C, A, B, F at a cost of 4. Let's look at it. S to C, the cost is -2. So we have -2. Then C to A. C to A. Okay? C to A. Oh, C to A is this. So that is 2. Then A to B is 1. Then B to F is 3. And this should give us -2 plus this is 0, plus 1 is 1, plus 3 is 4. And this brings us to the end of Bellman-Ford algorithm. I hope you understand this. Do it a number of times. Thank you.